But don't be shy. I'm missing something.
Dominating session.
From yesterday also? From yesterday also, of course.
Yesterday
But
afternoon.
there's 3, 6, and 4, 10 people here, and we had 12 talks. Who's missing?
The speaker between us.
Okay, there's one more person missing. Well, okay, I guess we'll carry on. So, please, let me just sort of remind you, maybe what you heard yesterday is now fading a little bit in your memory. So, yesterday we had 2 talks. 2 of them were on radial velocities, measurement of radial velocities and time to memory. The third talk was about post-ATP stars and the imaginary clouds. And today, of course, everything's fresh in your minds. I hope you have discussions about far infrared, what it's telling us, commercial. We learned about abundances and abundance gradients in the galaxy, maybe a relationship to morphology. Also, we learned a little bit about why it's important to track the, in order to track the mass around mass of the stars, we start by memory. We have to look at what, as we move into the interstellar medium, what's happening to them. And yeah, and then of course the last 3 talks about dust chemistry and interesting things, those are elements that resolve this. We got into the introduction. Okay, let's start with Jill.
Last things first, because I have a short memory. Izet and Rizard both presented interesting cases dominated by Wolf-Rayet type central stars involving dual dust chemistry outflows. The assumption usually is that it's the ultraviolet that's dominating the production of or in this case, the dissociation that you need to get the chemistry going. But there's an interesting possible alternative, which is X-ray emission. And so this is something we're investigating in the context of protoplanetary disks, where we see very interesting complex chemistry and can't all be explained by UV, because typically these are disks around low mass stars there's some accretion, some UV coming from accretion shocks and chromospheres, but not a lot. But there's a lot of X-rays coming from coronal activity in accretion shocks. And so that's thought to drive a lot of the chemistry. And the interesting connection, I think, here is that, as Mark showed in his poster yesterday, so far we are at a 100% detection rate of diffuse X-rays in Wolf-Rayet stars, 5 for 5. I hope we don't get cycled 16 times. It might break that streak, but no, I do hope we don't get cycled 16. But so I'm just wondering if this is, I think it is something that we need to put into the models at some point, just to see if it can affect the chemistry, especially if the production of things like C2H, which seem to be very prominent in protoplanetary disks. I'm afraid that we may get into a regime where things are too finely tuned, because you need to have the photons penetrate but not go through. And I think that's maybe the same issue with ultraviolet. So maybe you can comment about that just generally and what you think the challenges might be.
Yeah, so this is actually, there's another PhD student that I was working, we started at the same time, and she was actually working on this new code, and she was doing, so I was just using UV radiation, and she was actually using X-rays and PDR, so it was an XDR and a PDR, and she was finding, I guess, similar things. She hasn't to meet the paper, but I think it's pretty interesting, and she was doing this for NGC 6302 because of for using the carbon torsion ratio on this planetary, we still don't know if it's oxygen rich or carbon rich, but you have pHs, and the only way that you can excite them is through an X-ray source. So this is, we actually were supposed to be working on that, and sort of, but no, it's really interesting, and it would be good to maybe follow up that, because she's sadly leaving astronomy, so maybe, or I can try to do in the video code, because you could add in the video code the X-ray, XPDRs.
One of the other things that's emerging from the HER plans, combination of HER plans and Chan plans data, is that we seem to be seeing what should be X-ray generated chemistry in sources in which the X-rays don't seem to be there. So it implies that those effects may be long-lasting if they're there. I would argue that 6302 is an object where we don't see X-rays, but the X-rays were there back when the object was more like 7027.
Okay.
I'm going to add something about that. In our reference data, actually when I was looking at the average dust temperature, I was trying to find correlations between that and the presence or absence of diffuse X-ray emission. And there is no more when you look at the average dust temperature, but when you look at the resolved dust temperature, actually the temperature in the center where you see the diffuse X-ray emission, that correlates with the presence or absence of X-ray emission. So basically you have a higher temperature of the dust in that region based on that. And so also in my beta maps, where each translates into chemistry, I see a lot of kind of mixed chemistry. I see values of beta around 1.1, which shows carbon, and silicates much further away. So it's always like the carbon much closer to where the region of the X-ray emission is. So we can see that now, but I didn't have time to share that.
I'm not sure if, I don't know how observations of planetary nebulae X-rays, I mean how planetary nebulae were selected. I would expect that they are the brightest, like observed by Maizero.
Previous, before Champlans, yes. But the idea with Champlans, we're moving toward a volume-limited, unbiased sample.
Then it would be quite interesting to see if the sources from the Letizia sample are on your list. Then we can check if really X-ray is important for this double chemistry planetary, at least in the list.
Do you want to go? Compact. They're all more compact than 3 seconds, 4 seconds, and also they're not up there. Sorry, there is double chemistry. What can you do with compact writing? You can do that.
So we could do the opposite, right? So we could just do the opposite. We know which ones are separated, and we just gonna trace the pH, right? Just look back and see where they are, and if they're in the uploads or in the torrents, or just where the things reach. So that's pretty interesting.
I've seen some more hands behind Joel before. Some hands. Okay, go ahead.
Sorry, I'm changing the subject, but I want to discuss the things of the gradients from planetary nebulae, discrete galaxies, and I agree with this reporter that in our galaxy, in the Milky Way, the distance to the planetary nebula are not well known, so that makes that gradients very uncertain. But of course, the IR is going to help us, giving us much better distances to planetary nebulae. But the other thing I want to say is that I think there is increasing evidence that planetaries are modifying the oxygen. So using oxygen to estimate the gradient is very dangerous. I much insist in using other elements, neon and those non-elements that is not to be affected by the synthesis stars.
Well, you are absolutely right in saying that there is oxygen formation with oxygen arrangement also to planetary nebulae. But as I say in my talk, this is a zero order. The production of oxygen is much smaller than the gradient slope. I mean, so it's almost unimportant in this type of application, at least in the galaxy. You might be totally right if you go in a very low frequency, and then it may change quite a bit. So you have to be careful when you compare galaxies. To compare galaxies that are similar things. But if you go, like M33, we did that recently with M33, M33 is on average like LTC, metallicity. Down to the LTC metallicity, there is not much variation of the gradient.
About the oxygenation, I think it's not that complicated because they have also new, especially iron. They have basically the same behavior as oxygen. So sometimes people assume that oxygen is produced by already cycle. That's very probably a very small amount at this scale. And if you compare with new and larger, especially new and larger, you see that the results are not very good. Sulfur is, there is still some problem at the moment. So, the other point you raised is distances. I think distances used to be a stronger problem than it is now because there are several distance scales, they are quite different from each other. And so, for instance, what we do normally is to use several of these different scales and compare the results. So depending on your goals, the results will not change very much. So I believe that the distance problem will be solved with time very far. So this will put an end to this discussion between the different scales. But I don't think this is the main problem. The main problem is the ages and the real uncertainty of the gradients. This is one very important point. We all calculated gradients and estimate formal uncertainty, say like this squares calculated, things like that. But the real gradient is much larger.
Thank you. So there's a hand in the back somewhere. There in the back.
I have a question to Eva. The computed images that you show are very nice, but they don't look like the image I have of planetary nebulae. So, to what kind of images are they supposed to be comparable? To H-alpha images or to infrared images or what?
What I show there is density basically, so then you have calculated the emissivity of the material.
Okay, but is it
And
for...
the scale of the simulations I was showing is 4 parsecs. So we are talking about very large structures around the area.
Okay, but could that be also neutron gas, or I mean, where is the ionization front there?
The ionization front, it depends on the mass of the star. If you are dealing with a low mass star, you are vertically thin. At the end of the DNA evolution. If you go to the higher mass stars, you basically trap the ionization front that's in the middle. So for a high mass progenitor, you will have neutron material outside and the ionized front within the shells of the shell.
Okay, but and do you think, but perhaps it would be better than to show images of n square, which is the emission of H beta, for example, H alpha is n square, and really that would increase the differences, but I don't see so many objects like this.
The Gaussian shares are planetary nebula have been found in several objects already.
Yes,
And
but not generally. Whereas what you showed seemed to be something that should happen always, because any object is going with a certain velocity across a medium of a certain density. So I'm surprised that we don't see more of that.
As I showed today, there is the magnetic field is going to make a difference on that because you need to go to high velocity than we assumed before in order to be supersonic or supersonic. So that's one thing. The other thing is that you might have a projection effect if you are so going, if you see the structure from above, for example, going towards you, you are not going to see this effect. And also, I mean, we are looking about I'm talking about the faint structures around the nebula. I'm not talking about the bright shells, I'm talking about halos. And halos are hard to find, are hard to observe. So you have to go to, once you go to Herschel, it seems to be everywhere. Or at least more often than we thought before, and you see them in the stars. So, that I'm talking about relative velocity, when you stand on the gas. The star can be moving with the gas and you don't have this effect. So you need a relative velocity when you stand on the gas to have this effect. If you don't have it, you should have just a normal round planetary nebula. If the AGB is very high. And if the AGB must have this effect.
Can I just follow up just for this 1 second? So I had a question that yesterday the question was raised by Valentin and other people. Well, there are some objects where the total mass which you detect is very small, and we had some responses to that. Now, something might be lost because of the fact that these things are moving, and the stuff just is lost in the interstellar medium. Can you provide from your simulations estimates at different ages and different evolutionary phases, how much mass is undetectable just because it has been lost in the interstellar medium due to motion? That would be very useful.
Yeah, in fact, I have. In fact, we have estimated the masses that both when the star is at rest, what is the mass that you see around it, and is higher than the mass that you don't consider in the interstellar medium because you're creating material in the interstellar medium. And also, I mean, when the star is moving, yes, you basically remove most of the previous masses, and you only get the 10,000 the rest of the velocity and it's very easy.
Can you speak louder?
Closer. Sorry.
So basically what I think what you were saying is that you can lose a lot of mass because of this process and you would never see it. So
okay, but the question would be, for instance, in the case of Mile, which is the mass you estimate for the tail?
Yes.
Can you give us?
Not right now, but I can look at it. I haven't looked at the mass in the case, but I can do it. Yes. I have the mass there. I just have to add it. I will do it and then. I will do it and then.
I just wanted to add something about the detection rate for those motions, basically. So from the paper by Nick Cox about the masses of evolved stars survey, so the detection rate, if you go to a volume limited sample of 500 BC, it's 70%. So it's pretty high for AGB stars. And so we see them almost. So people who work in far start to believe that there are ubiquitous. You should see them almost everywhere. It's a matter of looking for them with the right sensitivity and resolution, basically. And so the same thing for our PA nebula, we're looking right now with also Herschel data. So it's quite common, but you need to look for them as well. So.
One thing, I'm not inventing the star. I mean, I'm just putting the star that the stellar evolution gives me. So, I mean, I'm not just doing anything weird with it. I'm just like, following the mass. I mean, that's the only thing I'm doing. So, I'm not adding any strange physics to the problem, or I'm just trying to add as much physics as possible without making very strong assumptions about the stars. So, this is what I get. I mean, if we don't observe it, maybe we have to look at it. Exactly. They are there.
okay, so any more? Oh, there's Bruce. Go ahead.
Lisa, is this on? I wonder, have you thought at all about how to test the hypothesis of CO ionization using ALMA? And if so, how would you go about it?
Do you want me to send the proposal? No, I don't know. I mean, I guess we're thinking of doing this, but we want to do it first with Apex because we want to detect first this in this area. And once we detect it and see where we are, then we can follow up with our But yeah, there's a plan on thinking about that and doing that. I don't know.
Amber? I'm seeing a hand way at the back, so next. Yeah, okay. You'll be after.
Okay, this is a different question I want to ask about Gaia. One of the things that noticed if you go to a resolution of microarc seconds, you go to superlinear orbits. Because say if you're going to send a star from orbit of 1 year, well, that's going to show a million passport. So is there any chance of us actually detecting binary orbits of relatively close binary systems in planetary nebulae?
Yes, in fact, the idea we do a lot of observation of binary stars, and we think that inside 1 kiloparsecs, this observation will be useful for determining binary companions in planets because of the resolution, but also because if they are bright enough, we will have also velocity variation, velocity variations. So yes, Gaia will probably contribute to the determination of binary proportion.